hello student to the foundation of classical electrodynamics course. So, under module 2 we today going to learn more about the Gauss's law. So, today we have class number 25. In the last class we started the Gauss's law. And in Gauss's law we mentioned that if we have a so the flux phi d phi for a given charge having electric field E is E dot ds. I have a charge here and I have a surface here, and say this charge is q and this is the direction, say n unit vector of the, and this is ds surface area. Then the amount of flux, if somebody calculate, is this one. Now, if I have an enclosed surface, any enclosed surface, and this point charge q is inside that, and if I calculate the total surface, total flux, that is total flux is say phi, that is the total surface integral of that quantity E dot ds, and that quantity we figure out is simply q divided by epsilon 0, exploiting the Coulomb's law. And since it is enclosing, the volume is this, so total surface is the surface that is enclosing this given volume. So, q is inside this volume, so I should write it as q enclose. Okay. So, the natural extension of these Gauss's law for a scattered charges. So, now we will do the same thing for bunch of, say, we will do that for bunch of charges that are scattered around. So, we have bunch of charges scattered around. So, instead of having one charge, now say I have a region where all the charges are scattered, q1, q2, q3, qk. Okay. These are the scattered charges, and for the scattered charges we know if I want to find out the electric field, total electric field, that should be the summation of the electric field for each individual charges at given point r. So, k goes to say 1 to n if there are n number of charges. Okay. So, this is my total electric field. By superposition principle we can say that. Now, if I want to find out what should be the total flux phi e, that is integration of E dot ds, and this is a closed surface integral because I am enclosing this surface, enclosing this volume with this surface, and now this E is this one, because I am taking the value for all the charge point. So, it should be summation of E k, and k goes to 1 to n dot ds. Okay. So, so simply we have for one charge, so I can have this like summation of k 1 to n that I put outside, and then it is integration of E k dot ds. Okay. So, this quantity is for each and every point charge which is here, and for that we know that value should be q k divided by epsilon 0 according to the Gauss's law. So, eventually I have my total flux phi e to be summation of k equal to 1 to n, and this quantity we know because this is the Gauss's law, that total surface integral, total closed surface integral ds flux is equal to q divided by epsilon 0, and we should write q enclosed if this is a single charge that is enclosed by this surface area. So, that quantity I just replaced by q k divided by epsilon 0. Now, this is nothing but 1 by epsilon 0 and summation of q k, k goes to 1 to n. Now, this quantity is my total charge that is enclosing. I write a big Q. This is a total charge, this is a total charge that we are having here. So, that means I simply have that the integration of the total field E dot ds for the scattered charge is simply q enclosed divided by epsilon 0. That is the expression we are having. This is the extension of the Gauss's law for scattered charges. Well, now we will go. So, I can write that the total flux, from here we can see that the total flux that is equal to phi e. The total flux phi e is independent of the size of the volume, right. Independent of the size of the volume, and only depends on the total charge. So, I can make different volume by just enclosing all this charge by drawing different kind of closed surface, but that does not matter. Whatever the volume is there, for all cases the total amount of flux is same, and it only determined by these term q enclosed. What is the amount of charge is enclosing, that matters. Okay. Okay. The next thing I like to discuss about, because we are going to discuss more about the Gauss's law, and we will see how these things happen when the charge point is inside or outside the closed surface. So, before doing that, let us try to understand the concept of solid angle. solid angle. The concept of solid angle. And the concept of solid angle is this: suppose I have a say line angle, this is called a section, line section AB, and this angle is say d theta, and this is r from here to here, from the point. So, the line angle is d theta, which is AB, this line segment, divided by r. Okay. Okay, let me write this A properly. This is A B divided by r. And if I want to find out the total line angle, it should be the integration of d theta, and that eventually give us 1 by r integration of whatever the line segment I am having, total integration of this quantity. And we know that this quantity is 2 pi r, because that is the periphery, divided by r, and we have the total line angle like 2 pi, okay, that we know. In a similar way, if I do the same problem for a surface, suppose I have a surface here, and then I have, this is the area, suppose this is the area, and this is ds. From here to here the length is r, radius r, and this is say O, and we have a angle here, we call it solid angle, which is d omega say. Now, how you will define this d omega? This d omega is equal to this area ds divided by r square. Okay. Now, if I want to find out the total omega, total solid angle, then it should be integration of d omega, and it should be 1 by r, then sorry, this is 1 by r square, and then we have the integration of these ds, and ds is now the total area, total surface, whatever the, if I have a closed surface, then it should be a total surface. Then it should be simply 1 by r square, then 4 pi r square, which gives us simply the value 4 pi. So, the solid angle seems to be 4 pi for the surface which is which is forming a closed region. So, in general, d omega is simply ds surface and then the unit vector of the surface dot unit vector of the r. So, let me put this unit vector r divided by r square, and if I want to find out the total solid angle omega, then I need to integrate it, and it should be 1 by r square and then n dot r unit vector ds, and that should be, if it is a closed region, then I should have a closed surface integral here. Okay, this is a closed surface integral. So, that is the definition we know. Now, let us try to understand the Gauss's law in this way. Suppose we have a charge, case 1, when the charge is inside the region, inside the volume, inside the closed region. So, this is a closed region, suppose I draw, and suppose the charge is sitting here some point q. So, if I want to find out what is the solid angle it will make this from this point, so I should have a area here and the r from this, from say here to here, this is a r, this is the unit along unit vector, it is r, from here to here the value is r, and the unit vector of the surface is along this direction. This is the direction of the surface, which is a vector quantity, and I write n. Okay. So, what is the flux for this small section? So, the flux is d phi, and if I calculate, it should be E dot ds, where E is the electric field exerted by this charge q. Now, from the Coulomb's law, I can know what is the value of electric field here if the distance is r, and that value is simply q divided by 4 pi epsilon 0, and then unit vector r divided by r square, that is this quantity, and then dot ds with the unit vector n, if it is having a unit vector this side. Now, that quantity I rewrite in a different way, like q by 4 pi epsilon 0, and the rest of the term I write in this way in the bracket, and that is 1 by r square and then n dot r unit vector and ds. Note that this quantity I just defined few minutes ago, that this quantity is my this d omega, right. So, this quantity is simply the solid angle that we know, and that is d of omega. Okay. So, flux d phi E is simply q divided by 4 pi epsilon 0 and d omega that we have. Now, if I want to find out the total flux, total flux is integration of d phi E, which is nothing but phi E, but this quantity if I integrate, then it should be q by 4 pi epsilon 0 and integration of d of omega, and that d of omega integration is nothing but the total solid angle. So, I have q divided by 4 pi epsilon 0 multiplied by 4 pi. So, for this 4 pi will cancel out and we have q divided by epsilon 0. Okay, that is the total flux. Now the next thing is what happened if the charge is outside. So, case 2, when charge is outside, what happened? If the charge is outside, the picture that we have, like before, I have a closed region, closed volume region, and suppose the charge is placed somewhere here. Say charge is placed somewhere here. So, this is my charge q, okay? And if I draw a line here, so this is the r vector I am drawing, this is my unit vector r, and then what is the solid angle it is exerting for this surface, that is this one, and this one. So, two solid angles are here, one is the area that we are having, this area, and another is this area. Okay. So, what is the unit vectors of this area? I quickly draw that one unit vector is along this direction, this is say n 1 unit vector, and another unit vector because it is opposite direction. So, in this direction this is n 2, this is the unit vector. I have this as n 2. Now, from here to here I have this length from here to here, this is r 1, and from here to here this length is say r. So, suppose the big one is say r 1 and small one say r 2. Okay, fine. So, what is my ds 1? ds 1, this is d vector ds 1 is ds 1 in 1 unit vector, and ds 2 is ds 2 and n 2 unit vector. This we know. Now, what is d omega here? So, d omega is same because it is exerting the same thing. So, I can write it, it is d is 1 vector dot r unit vector divided by r 1 square, that is again equal to d s 2 dot it is d s 2 dot, okay, I am having some issue with this, dot r unit vector divided by r 2 square, that quantity. So, d phi 1 is the flux due to this quantity, and that is this charge q divided by 4 pi epsilon 0, and then I have the area here ds vector dot r unit vector divided by r 1 square, and d phi 2, the flux due to this phi 2 S2 area, that is due to this area, is q divided by 4 pi epsilon 0. This quantity will remain unchanged. Then we have ds. So, this is ds 1. So, this is ds 2, and again r unit vector dot vector sign divided by r 2 square. Okay. So, now you can see two interesting thing, that this quantity and this quantity, they are same, I mean both are d omega, but the angle here is, so if I calculate s ds dot r unit vector and ds 1 dot r unit vector, then we need to take the angle here. But if I want to take the other ds 2 r unit vector, r is in this direction, so then my angle should be this one. Okay. So, that simply suggests that this d phi 1. So, whatever the d phi 1 I calculate and whatever the d phi 2 I calculate, this quantity and this is same quantity, but this quantity if I execute, then these are opposite, because there will be a negative sign associated with this, both are d omega. So, one case is d omega is positive and another case it is negative. So, eventually we have d phi 1 is equal to minus of d phi 2, because one is negative to other here, this portion. So, total flux if you calculate under this condition, which is d phi e due to this small segment, then it should be simply d phi 1 plus d phi 2, and this quantity is 0. So, that means if I calculate the total flux phi e, it will be simply 0 if the point charge is outside the volume. So, that means whatever the flux we have here in a, it is going in, the same amount of flux is going out, that is the physical meaning. So, since the amount of flux that is going in and the amount of flux that is going out, they are same. For the case when the charge is placing outside of this volume element, then that basically makes the total flux calculation 0. So, we do not have any electric field if we are having, I mean the total flux is equal to 0 if the point charge is outside. Okay. So, that is also consistent with the Gauss's law, because in Gauss's law you calculate, if you calculate the integral E dot ds, close integral E dot ds, then we say that it is the total integral is the q enclosed divided by epsilon 0. But in this case you can see that q is sitting outside, this is my q which is sitting outside. So, since it is not q enclosed, so we can say q enclosed is 0. So, that means if I calculate this quantity, integration of close integration of E dot ds for this charge, then I will find 0, because q enclosed is 0 here, this is which is consistent with the Gauss's law, and that we also mentioned here, we proved that with this figure that it is also 0. So, with that note I would like to conclude today's class, because I do not have much time today. So, in the next class we will try to understand the differential form of the Gauss's law and the corresponding calculation. So, thank you very much for your attention and see you in the next class.